Well, good morning. Happy Odin's Day. Hope you're doing well. We're going to look at an idea and basically just one big idea, and then we're going to do one big problem. So you've seen scatter plots before, and we're going to talk about the types of scatter plots that exist. You see the three here, and then we're going to investigate and graph a certain scatter plot and talk about something called the line of best fit. So I hope you do well. Let's dive right in. Please do draw what you see. Obviously, these dots don't have to be perfectly the way I have them, but just in that general sense. I believe we've discussed before that the first scatter plot would be called a positive correlation. And we've talked about slope before. So if you think about slope, we know that slope looks like that. If we were going to put the little man to the left of this, he'd be walking up that hill. Now, this positive correlation, what that means specifically is that both your x and y, or both the variables, are increasing. As the x increases, so does the y. The one in the middle is what we call a negative correlation. And if we think about slope, that should make sense to us. And what's happening during a negative correlation is that as one variable increases, the other is decreasing. And so these two situations, like the book talks about for positive correlation, like if a student was studying for the test, the number of hours they study, it likely correlates to them getting a higher grade. So the grade being the y, and the number of hours being the x. As I increase my number of hours, I increase my grade. A negative correlation might be the greater amount of hours that the student watches TV. That's the x, that's the input in preparation for his test. The lesser his grade is. So if he has to study for a test where he spends multiple hours watching TV instead, that's probably going to lessen his grade. The next one is what we call no correlation. And your book makes up some sort of thing like the third letter of the child's name in relationship to his score. There's no correlation there at all. However, many of the situations we look at in the real world either have a positive correlation or they have a negative correlation, at least the ones that matter. No correlation there's no connection to those things. So we're going to look at a situation in order to describe what's called the line of best fit. And basically think of a science situation in which we are measuring certain specimens. And I need you to make this chart. So we're going to measure the volume of the specimens in centimeters cubed, and we're going to measure the mass in grams. And so the volume of the specimens given to us are this list: 2, 4.5, 5.7, 10, 7.5, 6.9, 3.1, 9.4. And then once the mass was measured, we found that a volume, something that had 2 centimeters cubed, this particular specimen had this as a volume, 5.3, and then on down the line. So go ahead and fill out this chart: 12, 6.1, 27, 20.9, and 16.2, and 9 and 26. And yes, we are going to graph these. Now, I'm going to go to another page to do so, but just in your setup, you need a pretty big quadrant, but I just need the first quadrant. And we're going to obviously identify our x-axis as the volume measured in centimeters cubed, and then the mass in my y-axis being measured in grams. And I'm about to go to that next page, so I want you to see how this is going to be set up. Hopefully you're using a ruler. For the mass side, what I chose, and I think you should make the exact same choices basically, is that for every 2 is worth 5. So that's for the y-axis. So 5, then there would be 10, 15, which I don't mark, 20, I do mark. So I'm marking every 10, but I established that first 5. And then why don't we say every box on the volume side being worth 1. So you see me marking the 1 to establish, and then at my 5z's, 2, 3, 4, yeah, and at the 10, because that's all we're going to need. And then what we're going to do is we're going to graph each and every single one of these points. So I'm going to go ahead and begin this process. This is the first coordinate. It says 2, 5.3. So I'm eyeballing it right about there. 4.5, 12, right about there. 5.7, 16.1, right about there. 10, 27. 7.5, 20.9. 6.9, 16.2. 3.1, 9.0. And then lastly, 9.4, 26.0. Now, you can see that this situation is not perfectly linear. I often talk about Starbucks. If it's $3 for my coffee and I go in and I get one coffee, that's going to be $3. If I get three, it'll be $9. If I get four, it'll be $12. That is a perfectly linear situation. But real world data, such as measuring the specimens, its volume, and its mass, isn't necessarily perfectly linear. However, hopefully you can see that there's clearly a positive correlation here. So what we're going to do is we're going to take our trusty ruler, and I want you to line it up and try and line it up so you get as many points as possible. I'm going to draw a line that looks like that. Obviously, I have an arrow. Then, in order to draw the line of best fit, which we just did, well, our goal is to write an equation out of this. And so in order to write an equation, we need slope. So I'm going to identify a couple points that seem to be pretty directly on this line, such as this one. Oh, I'm sorry, let's mark this up. This is our line of best fit. And so now I'm going to identify some points that are either right on the line or very near the line. So I'm going to go with this point. And this point was our 9.426. And I'm also going to go with this point, that one. Because for me, that's where it were. Now, that one was our 5.7 and 16.1. Now, you guys are actually using a ruler, so you might have come up with different ones. I think we should just trust to go with these ones, even if for you it doesn't exactly look like that. You might go, what if I chose a couple different ones? Wouldn't that be okay? Yeah, actually, because we're going to be dealing with something where we're just kind of making a prediction. It's not dead in the water for sure. However, let's go with these points. 9.426, which was our very last point, and the 5.7, 16.1, which was our third point. Now, remember slope. Slope's going to be very important. And whenever I do slope, I want to do this 1, 2, x, y, x, y. I know we've done that before. And then the slope machine is y2 minus y1 over x2 minus x1. And then I identify my y2 as 16.1. I'm always going to subtract. And then my y1 is 26. And then I'm going to put that over. My x2 is 5.7. And my x1, always subtracting, is 9.4. Now, I'm going to actually just kind of approximate here. I'm just going to say 16 minus 26 instead of 16.1, which is approximately 10. This one I'm not giving any approximation. It's actually negative 10, sorry. This one would be precisely negative 3.7. Now, if you do the math on this, you'd be able to round it to the nearest tenth at approximately 2.7. So if you're like, wait, we wouldn't even do the math. I mean, go do the math. Go do 10 divided by 3.7. I promise you're going to come up at to the nearest tenth at 2.7. So that is our slope, right? Now remember, this all gets placed into a y equals mx plus b form, and the m being my slope. So what I'm going to do is plug in y equals 2.7x. Then I got to think about this b. Remember, the b is the y-intercept, but if you notice here, where this line crosses the y-axis is right down here at 0. Therefore, we have a y-intercept of 0. Remember, things that pass through the origin are going to fit direct variation form, and this is fitting that form, y equals kx, where the k is my constant of variation. A lot of this is a deep look into next year, and so I just kind of, because I won't be there with you, I wanted to fully teach you this idea, but it actually doesn't come up until I think 7.5. So, you're going to have different books. You'll get to this at some point. All right, so that's part one. We have written the equation to describe this situation. Now, part two is usually that they're going to ask you to predict. So even though we didn't actually measure this, the prediction is, what if I had something that had a volume of 100 centimeters cubed in volume? What would that be in its mass? So again, we're not going to draw this out. What we'll do is we'll just use our equation where our x, our input, is 100 centimeters cubed. And so I write, okay, y equals 2.7, 100, and then clearly I'm just moving the decimal place over twice, 1, 2, and so I could say 270, and then what is this? Mass, grams, so in mass, describing mass in grams. And so I would say, well, something that is 100 centimeters cubed in volume is likely to be 270 grams. And actually, if you think about this one, like, straight up, you're probably like, why did we all do all that work? Couldn't we have just concluded that if it's 10 in volume, it'll be 27. Well, if it's 100, wouldn't it be 270? Yeah. Hey. But notice how we didn't even use that point. We used different points. We used these points. And so it didn't end up mattering. And you might go, okay, well, so any of the points. Well, honestly, I might not choose this one because it's a little bit off the line. But any 2 points that are very near or close to the line should work for you. Hey, I hope you're well. I miss you guys a lot, and I will miss you even greater as time moves on. But right now, I am going to ask you, because it's Odin's Day, to just do standard homework, HW113. Bye.